Hello students, welcome to this module on complex variables and analysis part 4. This is part of the course CHE 641 at IIT Kanpur. So as we begin, we'll quickly recap what we have been doing very briefly so that we all get up to speed. We started discussing the idea of complex numbers. Complex numbers are an ordered pair of numbers usually represented by the letter Z, which is a plus ib or x plus iy, okay, where this is the real part of the complex number, b is the imaginary part of the complex number, right? I is square root of -1. Okay, this is the imaginary part unity, which is what helps us to generalize real numbers to complex numbers. I squared is -1. Note that the imaginary part of a complex number itself is a real quantity, and the multiplication by I makes it imaginary. Okay, there is a very basic formula which is called the Euler's formula, which we wrote in the last few lectures, wherein you know that e to the I theta is cos theta plus I sin theta. Okay. Now then, if you were to represent the complex number real and imaginary parts in polar coordinates, a is r cos theta, b is r sin theta, then z becomes r e to the I theta using this relation. This is called the polar representation of a complex number. So z is also written as the magnitude or absolute value or the modulus of the complex number times e to the I theta, where r is mod z. Okay, so these are all the various representations and notations used to represent complex numbers. Theta is called the angle or argument of a complex number. This is called the modulus or absolute value or magnitude of a complex number. Okay, so these are things that we just saw in the previous lectures. This is just a brief recap. Okay, so now one thing that we also discussed is important when you discuss the angle or argument of a complex number is to realize that this angle is usually between 0 less than theta less than 2 pi. Okay, or sometimes people also use minus pi less than theta less than or equal to 2 pi. We use this the first one in this course. So the key idea is to choose one and then stick to this so that you don't cause any confusion. Now we also discussed that if z is x plus iy, then the complex conjugate of z is x minus iy. In the polar form, if you write z is r e to the I theta, then the complex conjugate is r e to the minus I theta. So in order to get the complex conjugate, the I should go to minus I wherever it occurs, then you get the complex conjugate. Okay, whether it is in the Cartesian representation or the polar representation, all you have to do is change the sign of I to get the complex conjugate. Okay, then we also started discussing functions of complex variables. Suppose you think of a complex number z and it's allowed to vary, then it becomes a variable z. Okay, so we can think of functions of w is f of z. Okay, because z is x plus iy, which has real and imaginary parts. W, which will also have real and imaginary parts, is normally written as u plus iv. Okay, this is the real part of the function the complex function w. This is the imaginary part of the complex function w. And of course, the real parts, real and imaginary parts themselves are functions of the two variables x and y, which are the real and imaginary parts of the complex number x itself. Okay, so now one thing you can think about is you can write you can think of w as a function of two variables x, y, or you can also think of w instead of x and y. Okay, you can transform these two variables to z and z star, because you know that x is equal to half of z plus z star and y is equal to 1 by 2i of z minus z star. Just from the two equations, z star is x plus iy, z star is x minus iy, you can derive this, right? So instead of these two variables x and y, which are real and imaginary parts, you could imagine writing w as a function of z and z star. Okay, so if w is a function of x, y, right, then you can write dw as partial w partial x dx plus partial w partial y dy. Okay, now so if you write dw dz, therefore you will get from the previous discussion on partial derivatives, partial w partial x partial z plus partial w partial y partial z. Now partial x partial z from this expression, okay, is just half. Okay, this is half. Partial y partial z is 1 over 2i. This is 1 over 2i. Okay, let's go to a new sheet, then continue. Okay, so dw partial w partial z is nothing but half partial w partial x plus 1 by 2i partial w partial y. Okay, similarly you can write dw partial w partial z star, then you will get 1 by 2 partial w partial x minus 1 by 2i partial w partial y. Now in complex analysis or functions of complex variables, there is a special class of function called analytic functions. Now what are analytic functions? There are various ways in which you can define analytic functions. The simplest way is to say that w is a function only of z and not of z star. That is, you define analytic functions such that partial w partial z star is identically 0. This is the definition of analytic function. Okay, now if you do this, then you take this expression and set it to 0, you will get partial w partial x. Okay, let me just show this. So if you take this equation, then you will get partial w partial x is nothing but 1 by I partial w partial y. Or if I multiply numerator and denominator by I squared is minus 1, so partial w partial x, right? Sorry about this. Okay, partial w partial x is minus I partial w partial y, but w is u plus iv, so this is partial u partial x plus I partial v partial x is equal to minus I partial u partial y plus partial v partial y. So if you equate the real and imaginary parts of this equation, then one gets partial u partial x is partial v partial y and then partial u partial y is minus partial v partial x. These are the celebrated Cauchy-Riemann equations. Okay, this is very, very important in complex analysis, because these tell you when a given function is analytic, right? So these are called the Cauchy-Riemann equations. So if you have a function of a complex variable w is u plus iv, if this function were to be analytic, what is analytic? One way of thinking about analytic is w is a function only of z and not of z star. Okay, there are other ways of thinking about it. In the last lecture we told or discussed about how we thought about getting the limit to be unique as you approach a point if you want to calculate the derivative. This is another way of thinking about it, right? So w is u plus iv, then if the function is analytic, then u and v have to obey the Cauchy-Riemann equations or Cauchy-Riemann conditions. Okay, these are the Cauchy-Riemann conditions. All right, so this is very, very important because analytic functions have a very special place in the theory of complex functions and complex analysis, and you will see shortly the power of analytic functions as we go along in this course, right? So this also allows you to define if w is f of z is analytic, then dw by dz is well defined. That is the simplest. Now one simple way of thinking about it is if w is a function only of z, then partial w partial z is nothing but dw dz, because f is not a function of z star if it is analytic. Then this is also a function only of z, so this is also analytic, that is dw dz is analytic. And similarly higher derivatives of w are also analytic. So this is a very powerful result, because this is not the case in function of single variables. It is only there in the theory of complex functions. Okay, so the definition of analytic functions is that let me just so analytic functions, a function w of z is analytic in a given domain if that domain could be, let's say, a circle of some radius about the origin or anything that you want, if the function is single valued, continuous, and obeys the Cauchy-Riemann equations in that domain. Okay. So for example, if I write f of z is z squared, can you say whether it is analytic? Of course you can, by checking whether f of z, you can write z squared as x squared minus y squared after substituting z is equal to x plus iy plus 2i xy and so on, and then verifying whether this satisfies this is u, this is v without the I, right? You can check whether this satisfies the Cauchy-Riemann equations, or you can directly, readily by inspection, you can check this is a function only of z, so fz is analytic by definition. So just by inspection you can tell whether a function is analytic. Similarly, let's take another example. Let's take a second sheet. Okay, suppose I give a function f of xy is cos y minus I sin y. I ask the question whether it is analytic. Okay, so you can readily by inspection say that, see, y is z minus z star by 2i. So this means that this is a function of both z and z star, is a function of both z and z star, implying that this function is not analytic just by inspection. Okay. Of course, you can go ahead and verify from Cauchy-Riemann conditions as well. And similarly, let's take one more function. Is x squared plus y squared. Is this analytic? Well, you can readily verify that x squared plus y squared is z z star, because z is x plus iy, z star is x minus iy, z z star is x squared plus y squared. So clearly this is not an analytic, because this is a function of both z and z star. Okay, so this is one way of understanding how to check for analyticity. The fact that a function is analytic has huge implications, as I'll tell you. If a complex function f of z is analytic in a domain D, then all its higher derivatives are also analytic. So this has immediate implications in the sense that you can Taylor expand f of z very easily in that domain. It is f of z naught plus f prime of z naught times z minus z naught plus so on. Okay, so this is very easy to obtain a representation of a function, of that function, analytic function, about a point z0 using Taylor expansion, because we are guaranteed that all these higher derivatives exist. Okay, now the question is, suppose if I say that a function f of z obeys the CR equations, the Cauchy-Riemann conditions, in some domain D, then you can ask the question, will it obey in the entire complex plane? Will it obey CR, the Cauchy-Riemann conditions, in the entire complex plane or in other domains? Okay, that's the question you can ask. Well, it's not easy to answer, because in principle anything can happen outside this domain D, but usually what happens is that there are in the complex plane, right, there are isolated points where the function the Cauchy-Riemann conditions will not be satisfied, and elsewhere the Cauchy-Riemann conditions will be satisfied. So these points where the Cauchy-Riemann conditions are not satisfied, they are called the singularities of the function f of z. They are called the singularities of the function f of z. Okay, and singularities play a very, very important role, as you will see shortly, in many aspects of complex functions. Okay. Now, at these isolated points, at these singularities, the continuity of at these singularities, the continuity of partial derivatives breaks down. Okay, and that's the reason why you find that the CR equations break down at isolated points. Okay, so you can, let's say you have a function 1 over z. Just by visible inspection, you would think that it is analytic because it's a function only of z. Yes, so you may say that, well, what is the issue, right? How do you know that it has a singularity? Now, if you think of 1 over z as z star by z z star, I am multiplying and dividing by z star, which is x minus iy by x squared plus y squared. So you have u of xy as x by x squared plus y squared, v of xy is equal to minus y by x squared plus y squared. You will find that the Cauchy-Riemann, the derivatives partial u partial x is equal to partial v partial y is y squared minus x squared by x squared plus y squared, the whole squared, but at the origin, as you approach the origin, 0, 0, x equal to 0, y equal to 0, the partial derivative ux, okay, as you approach along the x-axis, it will blow up as minus 1 over x squared as you approach origin along the x-axis. On the other hand, partial v partial y will go as if you look at along the y-axis, if you take x equal to 0, you will get minus 1 over y squared, or 1 over y squared, I'm sorry. Okay, so the way in which these these functions or the partial derivatives, although they are equal everywhere else, at the origin you know that they are not the same. So at the origin, the CR equations are not valid. The CR equations, the CR equations break down at a singularity because the function or its derivatives which appear in the CR equations become ill-defined as we approach the singularity. Okay, so this is something that you must keep in mind when you think about analytic functions. Okay, so now the singularities of the analytic functions we discussed. Let me take a new sheet. Are of three types. What are the types of singularities? Singularities of complex functions or analytic functions. Okay, one is called a simple pole. This is the most commonly encountered or most widely encountered. A simple pole is of the form f of z is 1 over z, or more generally f of z is of the form 1 over z minus z naught. Okay, this is an example of a simple pole. Okay, so if f of z is c upon z minus z naught, okay, for a first order pole, this is called the residue of the function at z naught. Residue is what is left over, so this is called the residue. Okay, now if you think of this function 1 over z plus I into z minus I, there are two poles. One at z is equal to I, one at z is equal to minus I. Okay, now as we approach z is equal to plus I, then the first factor, as z approaches I, the first factor will become 1 over 2I. The second factor will diverge as 1 over z minus I. Okay, so the residue of the function at z is equal to plus I is nothing but whatever multiplies the pole 1 over z minus I, this is 1 over 2I. Okay, similarly the residue of the function at z is equal to minus I will be minus 1 over 2I, which you can verify yourself. Okay, so poles and residues also are very, very important. In general, the residue of if a function has a simple pole, at z is equal to z naught, then the residue r at z naught is given by limit z goes to z naught times z of z minus z naught times f of z. This is the general formula for finding residue about a simple pole. It's a very useful formula, as you will see shortly. Okay, let me draw a rectangle. is a very important useful formula that we will keep using. Okay, this is called the residue of a pole about a simple pole. Now you can generalize the notion of a pole to an nth order pole where f of z will behave as r of z naught by z minus z naught whole to the n. Okay, so this is the if the denominator has a power n, it's called an nth order pole. Now these are called pole singularities. Now we also occasionally encounter what is called an essential singularity. What is an essential singularity? This means that you cannot multiply this, you eliminate the singularity by multiplying, let's say the singularity is at z naught. You cannot simply multiply by z minus z naught to the power n and eliminate it. Unlike in the case of an nth order pole, where if you multiply this expression by z minus z naught to the power n, you will get rid of the singularity. One example is f of z. Example of an essential singularity is nothing but 0 to infinity 1 over z to the n factorial. This is e to the 1 over z. This has an essential singularity at the origin. Okay. The third type of singularities or branch points. You know that, for example, f of z is z to the half. This is a multi-valued function because in order for the same, suppose you go around in the z plane from 0 to 2 pi, in the w is equal to f of z, let's say in the w plane you would have traversed only 1/2. So as you go around the z plane once more, you will again fully traverse the w plane fully. That means there are two routes. So the same point in the z plane will now map to two different points in the w plane. So these functions are multi-valued functions because the same point in the z plane gives rise to two different values. So in order to make sure that you have a single valued function, as I told you, we will decide that you will keep a cut in the complex plane, in the z complex z plane, wherein you agree not to cross that cut. That is called a branch cut. Okay, the branch cut emanates or originates from what is called a branch point. What is a branch point? The branch point is that point wherein if you take the path around the branch point, only then you suffer this multiplicity of this function. Suppose I were to take, let me take an example here. Okay. So you take a circle about the origin for this function, then it suffers multiplicity. Suppose I take a circular path, okay, which does not involve the origin, then you will find that there is no multiplicity of f of z. So the branch point is a very important point because it is closed paths around that which leads to multiplicity. Okay, so these are the three kinds of singularities. Why are singularities important? Singularities are important because you know that in order for a function to be analytic, it should be single valued. Okay, and so the branch cut singularity or a branch point singularity is important because unless you decide on a branch cut, you cannot ensure that the original function remains analytic. Otherwise, the function will get multiple valued, and that will not remain analytic. Okay, so I will stop here. This is basically a quick recap of what we have been doing in the last 3 modules. Hopefully, hopefully things are much more clearer now, and I will start with the theory of complex integration from the next module. Okay, bye.